This is a short tutorial about equivalence of type class methods given certain laws. For instance, I would explain why flatMap is equivalent to flatten and map. The code examples will be in Scala. One can often hear that monads can be defined in different ways equivalently. It can be defined that a monad has pure map and flatten methods, or that the monad has pure and flatMap methods. And one hears that it's equivalent if you define like this or like this. Here is an article about monads that introduced most of this terminology, and it says often monads are defined not in terms of unit and star, but in terms of unit, join, and map. Now star is a function that was equivalent to flatMap in Wadler's notation in that paper, and unit was equivalent to pure. Join is equivalent to flatten. The three monad laws are replaced by the first 7 of the 8 laws above. If one defines star by the 8 laws, then the 3 monad laws follow. Hence, the two definitions are equivalent. Now that, in my view, is quite confusing. It's not clear why the definitions of some functions are equivalent just because some laws follow, and it's not clear what it means even that functions are equivalent. My personal encounter with this started when I read the book by Kuisano and Bjarnason, Functional Programming in Scala, which says this. There's an exercise that I wanted to solve. Show that the formulation using unit and apply is equivalent to the formulation using unit and map2 by defining map and map2 in terms of unit and apply. Establish that apply can be implemented in terms of map2 and unit. So I implemented these functions, but I still didn't understand what it means that this is equivalent. This formulation is equivalent in expressiveness. What does it really mean? Yes, you can express one through the other, you can express the second through the first, but what does it really mean? And my questions, for example, were, so what does it mean that x is equivalent in expressiveness to y? X and y are some values. In functional programming, functions are values. So there's some value x and the value y. What does it mean that they're equivalent? Do we say that 5 is equivalent to 10? We don't. So why do we say this here? And second question is, how can it be at all that the function like map2 that has 3 type parameters is equivalent to a function such as apply, which I denote app here, which has only 2 type parameters? So how can this be? It seems to be impossible. A function with 3 type parameters has a lot more freedom. There are a lot more of these functions than function with 2 type parameters. So this tutorial is my answer to these questions. First I will give a few more examples. So flatMap is called in Scala flatMap because of the composition of flatten and map. And so yes, we can express flatten through flatMap and flatMap through flatten. So here's how I would do this. If f is some type constructor that has these methods, then flatten can be expressed like this, and flatMap can be expressed like this. So it's indeed just map and then flatten. I developed a special short notation for reasoning about code. So in this notation, I would write it like this. Flatten is flat map of identity, and then p to which I apply flat map is equal to p to which I apply map of f, that's denoted like this, and flatten. So the notation basically is that this triangle symbol is the same as the dot in Scala, which means that this value is being substituted into a function to the right. And in Scala 2.13 and in Scala 3, there is a library function called pipe, where you just write xpipe f, and so that is the pipe operator that I denote by the triangle. And the up arrow is the map, is the lifting of a function to the functor f. So this is the notation that I will use, but I will also write Scala code just so that you can compare and see how this works in the notation. Another example, actually a very useful one because it's a very simple example, is how the pure method can be expressed via a value that is called wrapped unit. So WU is wrapped unit. It's a unit type wrapped in a type constructor f. So if we write this code, then we express wrapped unit through pure. It's just a unit value, which is an argument of pure, so that's a result of this type. And pure can be expressed through wrapped unit. So that's the code. Indeed, this is a very useful example that I will go through in detail in this tutorial, where a method with a type parameter is equivalent to just a value with no type parameters. And the third example is a bit more involved, is the filter method, which can be expressed through a function called deflate. Now this function may not be very well known, but the function deflate has a type signature of f of option A going to f of A, where filter has a more complicated type signature. It has f of A, it has a predicate A to Boolean. There's no predicate here. So it's a much simpler function. And yet you can express one through the other, because here this option A corresponds to the fact that sometimes this predicate could be true and sometimes it's false. And when it's false, then we need to remove the value from the collection. That's the meaning of filter. And so then we'll have a none in this option. So in this way you can see intuitively that these functions really express the same functionality, but this code defines one through the other in a straightforward way. So there are all these examples where different type class methods are equivalent. So this is a monad type class, this is the pointed type class, and this is the filterable type class. So there are other examples as well. So let's now talk about my confusion, which is, first of all, what is this equivalence? Yes, we can express flatten through flatMap, but so what? We can express 5 through 10, and we can express 10 through 5. Here's the code where I express 5, integer 5, through 10, and I express integer 10 through 5. So does it help us in any way to say that 5 is equivalent to 10 in expressive power? You would never say this. 5 and 10 are just different values. They're not equivalent or inequivalent, they're just different values. They don't have expressive power, really. They're just equivalent. Sorry, they're just numbers. They're not. You wouldn't say that they're equivalent. So what does it mean? Now I will answer this question by saying that we actually should not talk about it like this. We should not say that the function flatten is equivalent to function flatMap. That is meaningless. This is just as meaningless as saying that the number 5 is equivalent to the number 10. So we should not say that. But what should we say? Well, I will show that in a few slides. But basically this confusion is resolved by saying that we will not talk about it in this way. We will not say that the function itself is equivalent to another function. And the issue too is that it is implausible that this equivalence can work. And here is a simple example that I was talking about. There's a function called pure. It has a type parameter a and a wrapped unit which has no type parameters. How can they be equivalent? So An extra type parameter means there are many more implementations possible of this function, with all kinds of types doing different things. So here's an example. It's a bad pure function, it's a function we should not be using, but it has the right type signature. So if the type is integer, then we return a list where we have added a number 123 to the integer. Otherwise, we just return a list of a single element. Now, this is a perfectly purely functional implementation of this type signature. And there are many more like this. We could take different types, we could add different numbers, or we could do other things. So for integer, we could create a list of 3 elements, for example. Or we could even create a list of as many elements as this integer. We could do all kinds of things. With the wrapped unit, there are not so many things we could do. We could do a list of a unit, we could do a list of 2 units, a list of 3 units, but that's about it. So how can this be that functions with this type signature are equivalent to values of this type? They cannot be equivalent as types. So there are many more functions of this type than values of this type. And also, if I use the code shown here to restore the pure function from wrapped unit, I will fail to do so in this example. So this example will give me a corresponding wrapped unit, which is just a list of a single unit, because I will be in this case for unit type. And then I come back from the wrapped unit to pure, and then I get a list of a single element for all types. So that's not going to be the same function. And so, in other words, we cannot express this through wrapped unit. So clearly the type signature is much richer, and it allows implementations that cannot be expressed through that code. So the answer to this confusion is that the set of all functions of this type signature is certainly quite a bit bigger than the set of all values of this type. And these sets are not equivalent, they're not one-to-one. But so something is missing if something is equivalent. So what is missing is the naturality law. And to understand that, let's look at this bad pure, and let's see that the problem with it is that it does not work in the same way for all types. It works for integer types differently than for all other types. So I call this code not fully parametric. Now this code is purely functional, does not have any side effects, but it is not fully parametric because it does not work in the same way for all types in the type parameters. So code that works in the same way for all types in their type parameters, that's what I call fully parametric. To enforce that the function is fully parametric, we can require a naturality law. In the case of the pure method, this is the law. You apply an arbitrary function to the argument, and the pure of this must be equal to pure of x with map of f applied afterwards. Now in the code notation, it looks like this, or where you say x to which you apply f to which you apply pure is equal to x to which you apply pure to which you apply map of f. And you can omit x because it's a common arbitrary argument, and then it's this notation where this is the forward composition of functions, and I'm putting in the type parameter as a superscript. And this is a type diagram that illustrates how this equation works. So this equation is a composition of pure with type parameter a that goes from a to f of a, and the map of f that gives you f of b, so that's one path through the diagram, which is this composition, and the second path through the diagram is first f and then pure of b. Now pure of b is mapping b into f of b, and so you have the same type at the end. So this is the equation between two functions going from a to f of b. And that's the type diagram that helps us remember all the types and the type parameters that need to be used. So this naturality law will not hold for this bad pure function. That can be checked by just running this code. You can have a certain function here with some integer parameter, and this just won't work. And the naturality laws enforce this intuitive idea that a function's code works in the same way for all types. And for each type parameter in a function, you can write a naturality law. So now we can formulate the precise meaning of what it means that pure of A and wrapped unit have equivalent expressive power. And the formulation is that you have to consider the set of all functions with this type signature that satisfy the naturality law that is shown here. And then you consider the set of all values, wrapped unit, that you can have, and there's no law for those. So these two sets must have a one-to-one correspondence between them. So they must be in a one-to-one correspondence. That is the meaning of expressive power. All possible functions of this type signature that satisfy the naturality law and all possible values of this type. These are equivalent. For each one of these, you have one of these, and for each one of these, you have one of these. And you can have this proof for this. You can prove rigorously that this is true. In order to prove, you have to do two things. First, you start with some function pure that satisfies the naturality law. You define the wrapped unit value like this. So the code, we already know what the code is that connects these two. So you start with some function pure that satisfies the naturality law. Then you define the wrapped unit from it. Then you define a different function pure, let's call it pure2, from that wrapped unit. And you have to show that you get back to the same function you started with. So that pure2 is the same as pure. So to prove this, you apply that function pure2 to an arbitrary argument x, and you simplify the code, and you need to show that this is equal to pure of x. I wrote this proof here, and this is probably hard to read because of the unfamiliar notation. But this notation is one-to-one, just Scala code, where you have, for example, this wrapped unit dot map of this function, and unit value pipe pure pipe or dot map and so on. So I will not go through this derivation in this notation, but you could go through the code and substitute symbolically the code of wrapped unit, the code of pure2, and simplify symbolically the way that the compiler will evaluate this code. You can evaluate it symbolically and find that it's always going to be equal to pure of x. And during this derivation, you need to use the naturality law of pure, because otherwise you cannot show that they're equal. So at some point you will use it, and if naturality law did not hold, you would not be able to prove that this function is equal to that. And we have seen on an example, this is not true without naturality law. So this is the first thing you have to show. And the second thing you have to show is the opposite direction of the one-to-one correspondence. That you start with some wrapped unit value, define a pure out of it through this code, then you define a different wrapped unit value from that pure, and you show that you get back the first one, the one you started with. And this is a derivation. Now, in this derivation, you have to use a property that the identity function under map, lifted to a functor, is again identity function. So that is a law of a map function. So you have to use that law, and then you get the result. finally, you have to show that when you take some arbitrary wrapped unit and transform it into the pure function, that pure function will always satisfy the naturality law. In other words, it will satisfy where is it? That law. So this is another derivation that you have to do, because otherwise you could start with some wrapped unit, you do this to get a pure, and this pure doesn't satisfy the naturality law, so you do not have a one-to-one correspondence that you claimed to have. Because the one-to-one correspondence is only between the functions pure with this type signature that satisfy the naturality law and these. So this is another derivation you have to do, and I will not go through them because it's technical, and you could write out again the entire Scala code. It will be, excuse me, it will be just longer. It will be longer to write this code than to write the code notation that I'm using. But this notation certainly looks weird, and now I don't want to go through it in detail. So a general pattern is that you want to prove equivalence of some functions with some type parameters under assumption of naturality laws. So how do you prove? You have to show that you can implement one function through the other. So you implement functions from this type to that type and back. So these are these two functions, p to q and q to p. You show that the composition of these functions in both directions is identity. So if you start with some p, you get q out of it, and you get p out of that. That's the same p you started with. And you start with some q, and you get p out of it, and you get q out of that. You end up with the same q. You have to prove this. And you have to prove that if you start with some p and you get a q out of it, that q will satisfy the required naturality laws, and also same for p. So if you start with q and you get a p out of that, it should satisfy p's naturality laws. So these are the things you have to do in order to prove this equivalence. Just a remark that this idea of having a set of all functions of a given type that additionally satisfy a law. Now this is not the same as just having a type signature. It's called a refined type. It's a type with a refinement or a restriction. So we do not admit all functions of this type, all values of this type. We only admit those that satisfy some equation, which is what we need to do when we are in this business of equivalence under laws. We need to impose some law or some equation on these functions. And the Scala compiler cannot verify those laws. These laws cannot be formulated as just a type. It has to be a refined type, a type with an equation next to it. And the Scala compiler cannot verify those equations. Also, you cannot verify those equations in tests. So you can write tests, but the equations should work with all types at the same, in the same way. But you cannot run tests for all types. You can only run tests for specific chosen types. Type parameters cannot be arbitrary in your tests. You have to choose certain types. And so you could not possibly verify, for example, that this function doesn't have somewhere code like this that is looking for a very specific type and does something weird with that. You could not know what this type is necessarily. And you could not include sufficiently many tests. So testing is unable to verify laws of this kind, because these laws have arbitrary types in them. So in order to verify laws, you have to perform symbolic reasoning about this code. So this is what I did here, although I did not write code. You could, it just be a lot longer to write code, but this is just a very short notation for Scala code with .map, with unit values and so on. So you can do this by hand. You can do this symbolic reasoning by hand and prove the laws. Let me give you a few more examples. of how this works. So the equivalence of flatten and flatMap actually requires a specific naturality law for flatMap with respect to the type parameter b. And this law transforms the type parameter b. So it has this form. You add a function f, which is arbitrary, and it should be the same as you first transform with f and then flatMap. In the shortcode notation, the law is written like this. Another example is equivalence of app and zip. So these are applicative methods. Both of them have two type parameters. So their equivalence requires a naturality law for each one. So if there's a naturality law for app that is required, and there's a naturality law for zip that is required. So this zip with respect to parameter a. The first one you transform, and then the same result should be when you transform this one. And for app, it is the type parameter b that is being changed here, because you're doing a dot map on the result of app, which has type f of b. So then it's a function f of type b to c. So that is not obvious that you actually need these two laws, and unless you assume these two laws, the applicative method app is not equivalent to the method zip. So, and the proof of this equivalence is long, because you have to use these complicated laws, and you have to prove both directions, and you have to prove all kinds of things. So, like I said here, you have to prove 3 things if you want to prove equivalence, and that's what you need to do, and that's a lot of work. So let me conclude. I formulated rigorously what it means that some methods have equivalent expressive power. Actually, it's not the methods that have equivalence, it's the refined types that you have to formulate that have a one-to-one correspondence. So these equivalence only holds after imposing some naturality laws. Almost always you have a naturality law. Unless you do that, it just is not correct that they are equivalent. Naturality laws constrain code. They eliminate sometimes type parameters. So we have seen examples where you have equivalence between methods with 2 type parameters, methods with 1 type parameter, or method with 1 type parameter, method with no type parameters. So this kind of equivalence can eliminate a type parameter. When you eliminate a type parameter, you get a simpler type signature and a function that is usually simpler to reason about. And so proofs of laws are often simpler for those functions that have fewer type parameters. So for instance, flatten has just 1 type parameter, flatMap has 2. It's easier to prove laws for flatten, for specific monads, than to prove laws for flatMap. I should mention that naturality laws usually hold automatically. You usually do not need to verify them, because your code is usually fully parametric. But if it is not fully parametric, if it has side effects, if it has other things, you have to verify that naturality laws hold. A lot more details are given in my book that I'm finishing now. This book is available in the source code and the PDF for free. This book explains with a lot of examples and exercises what are the techniques of symbolic derivation, symbolic reasoning about types, symbolic reasoning with code, how to derive these laws and verify them by hand using this short code notation, because if you don't use it, you will just spend 10 times as much time trying to prove the laws. So I have hundreds of examples and hundreds of proofs that I show step by step in this book in order to teach how to do this. And of course, in each case, I give real-life motivations and applications of these techniques. So these techniques are not just fun or for spending time. There are reasons why you want to do this, and one reason is that type classes can be defined more easily if you find a function that's easier to define, or even code can be generated automatically for some of these functions that have an easier type signature, and then you can derive all other functions automatically from that one. And you have, since you have proved the equivalence. Now, in this book, I show all the proofs pretty much in all detail, and I show how to reason about these laws in detail. So this concludes the tutorial.